put that in your notes. It's not in the slide, but it is in the notes. This note is exactly the same as a one sample means test, but we are working with a data set of differences. So again, make sure you highlight that, make sure you understand this concept. It makes your life really simple because I made the comment in the previous video, you already knew what to do. For the most part, you did, but I had to give you a couple new test statistics. It was, new calculations. It was kind of a more complicated problem. This one isn't at all. This one's straightforward. This is literally the exact same thing once you've established that you have dependent data and you've taken those differences. Notice you'll see here, these look exactly like before. Notice I'm adding subscript D. I'm doing that because I'm reminding myself that we are working with differences. Why is that? Because we start subscripting everything moving forward. This is going to be a thing we're doing here in chapter 10, and we're going to do it in the chapters to come as well. We have to start subscripting because we're going to have lots of things running around. So in chapter 9, that was less of a big deal. You could just put P, P hat, mu, X bar, whatever your stats were. It was no big deal. Okay, but now we got to start subscripting because we're in 2 samples, and then we're going to have more samples, more categories, things like that as we move forward. And so we've got to keep things straight. So in that last chapter, we did P1, P2, P hat 1, P hat 2, or we change it to the letter for the context of the problem. In these, we just always do it sub D, just to remind us that we're working with a group of differences. And again, we're contrasting that with the next chapter with independent samples, where we have each sample we average first and then we subtract, because we're taking the average of the actual, like on that one, we're going to take the average of column 1 and the average of column 2. And so we have to have X bar 1 and X bar 2, but now we don't do that, right? In this one, we're going to subtract first. That's a key thing to make sure we're aware of here, is that in a dependent problem, we subtract first. We create a new third column. We ignore the first 2, and I'm only working with that column of differences. I have to subtract first. Okay, so make sure we understand that. Our conditions are going to look very similar. We do have to add one thing to our conditions, though, and that is that along with our sampling methodology, we have to make sure that we do have dependent data, right? And that should just kind of make sense. That was one of the first things we ask when we have these types of problems: do we have dependent or independent data? So we just want to check off like, hey, we're in the dependent case. That's what allows me to do this type of work. And then the rest of it's going to be the exact same thing, except with subscriptees, right? We need our statistic to have a normal distribution. Again, super, super important. Why is that? Because when we go to our t-table, a t-distribution is a normal distribution. And so if my sample statistic here, X bar, is normally distributed, the value that I get from the t-table is good. If I don't have X bar normally distributed, the value that we get from the t-table is bad. Okay, so that's why this is important. How do we check this? We check this the exact same way we did before. If we start off with normality, then we have normality for our statistic. If we start off with our initial data is normal, then our sample statistic X bar sub D is normal. If not, then we check our sample size. Again, we don't have to deal with what the sample size of one versus the other is, because again, we're subtracting the 2 columns to get a third column, and then we can, like I said, you could literally delete those first 2 columns. I do not care about them anymore. Okay, so how do I apply central limit theorem? I've got that third column now that I'm working with. What's its sample size, right? If it's greater than 30, that's good. If it's less than 30, that's bad. That's if I know nothing about the skewness, as we're always talking about. If we have a skewed data set, we need more than 30, might need 50, might need 60, something like that. If we have symmetry, we don't even need 30, something like 20 would be fine. So it's the same thing we did before. Our test statistic is going to look just like it did before, except now I'm subscripting everything with sub D. It's X bar sub D, it's S sub D, it's N sub D. It's how many observations do we have in that differences column. It's what's the standard deviation of that differences column, and it's what's the mean of that differences column. But it's the same idea as before. It's X bar over S divided by square root of N. Rejection region and p-value are going to be the exact same thing. Again, you're working a one sample means test on that third column. So it's find the rejection region p-value just like you did in chapter 9, and then how we finish the problem off is the same as always. This literally doesn't change no matter what type of test we do. We fall in the rejection region and we have a small p-value so we can reject, or we don't fall in the rejection region, we have a large p-value, we fail to reject. If you reject, you conclude the alternative. If you fail to reject, you cannot conclude the alternative. So there's only one example here. Why is there only one example? Because we've done a ton of these examples already, done tons of homework on them. So um, if you want to jump ahead right now, pause, see if you can work this one on your own. I think that's not a bad idea because you should be able to. If you don't want to, again, no pressure, that's fine. Work through this here with me, but there's not a second example for you to come back to on that because I think you should be able to figure this one out relatively quickly, given that we did all this stuff in chapter 9. So when I read this question, as we're always talking about, how do I know what type of problem it is? You've already seen this example. Previously, we identified this as a dependent sample. Let me first back up and say, how did I identify it as two sample, right? Because I need to be able to say, is it one sample, is it two sample, is it mean or proportion? Well, you see mean right here, so that kind of gives that away. How do I know if it's one sample or two sample? Because we did something 12 times for dominant hand and we did something 12 times for non-dominant hand. So we did something two different times and there's not fixed numbers for each one. It's like this will be, if we got 12 more students, this would give you different numbers and this would give you different numbers. So we talked about that. How do I know if it's one sample or two sample? In a one sample case, I'm doing something and if I were to do it again, I might get different numbers, but the thing I'm comparing it to doesn't change, right? It's, is the proportion of people that are going to vote for a certain candidate more than 50%. If I get new people, the sample proportion would change, but the 50% still 50%. That's still the number I'm comparing to. That's one sample. Two sample is the proportion of people in this state voting for this candidate different from a different state. Well, when I get two new groups of people, I get two different sets of answers. That makes it two sample. Same thing here. If I were to do the same experiment over again, I'd get a whole different set of numbers for this and a whole different set of numbers for this. So this is why it's two sample. And then specifically, as we already talked about, why is it dependent? Because I have natural pairing. Each person has their own pair literally on their body. So that's what tells me this is a two sample dependent means test. I have the mean of the differences here and the standard deviation of differences here. And I have the number of differences listed here. So this one should work pretty straightforward. Note, you could see raw data in the form of here are the 12 observations for dominant hands, here are the 12 observations for non-dominant hands, then you would be asked to then go to Excel or some other program and actually do the subtractions, then find the mean of that third column, and then find the standard deviation of that third column. I've just shortcutted you here and said, I've already done that work for you. Here's what the mean of that third column was, and here's what the standard deviation was. You may have to do that extra step on certain problems, you may not. Okay, it's just going to be problem by problem. And so we set up our hypotheses. We have a less than hypothesis here. So we want to see, are the differences less than 0? Why is it 0? Notice the number, we kind of skipped over this on the previous page. The numbers could be different. Those are weird cases though. Generally what we want to know is one different from the other? And so in that case, when we subtract, we're comparing the subtraction to 0. So this is going to be the case we're working with. So it's, if you're asking yourself, could it be another number? Yes, it could. It's a very rare case. It's not one that we're going to talk about. That would be if I said, is the reaction time in individual's dominant hand, better than the non-dominant hand by 10 seconds or something. So we could compare to other numbers. But for the most part, we typically just want to see is one better than the other, is one different from the other. And so the number we're comparing to is 0. Check our sampling methodology. Which hand goes first? Is this good sampling? This is just something to think about. There's no right or wrong answer, I think. But if we have the same experiment happening twice, you might do better the second time because you kind of know what to expect. So if you're always having one hand go first, that might skew your results a little bit. In a perfect world, what you do is you'd randomize that, and so half the people would use their dominant hand first, half of them would use it second. So these are just things to think about, right? Like when you have anything with reaction times, you think if you're doing something, or you're not even reaction times, we can just expand it. Anytime you're dealing with people and people do something twice, they typically get better the second time, right? And so we would want to make sure that we're kind of splitting that equally between the two groups, and the two groups here are dominant hand, non-dominant hand. So again, just something to think about here. We don't know. The problem doesn't say how we did, so this is just something to kind of think about. Like we would want to make sure that we have good sampling here. We've already covered the data are dependent. We know nothing about normality, and we have a small sample size, so this is a little bit of concern. Now, if we had symmetry, 12 would probably be a big enough sample size, but we have none of that information in the problem. So again, just something to kind of think about here. Normality or symmetry would go a long way to making us feel better about our results. Without that, then we might have a little bit of concern there too. So again, just some things to kind of grapple with as you're thinking through these assumptions. Our test statistic, again, from here it should be pretty downhill. I'm going to subscript with the degrees of freedom. Just like before, we have a sample size of 12. Again, not 24, right? Again, delete those first two columns, ignore them. We just have that third column left, so we just have 12 people. So I don't care that there were 12 in each column because I only care about the differences. There are 12 differences, right? So that means my sample size is 12. My degrees of freedom are 11. Again, the mu naught is that 0 that we put in the hypothesis. And you should get that test statistic. We have a less than test, so that is left-tailed, so we get to put all of our alpha over there. We aren't given an alpha, so again, we default to 0.05, which would lead us to the critical value, negative 1.796. And again, if we were to draw where our test statistic would, draw this out, actually put the line right, put that line over here, negative 2.3 something, somewhere over here in the rejection region, so we know we're going to reject. That means we should get a small p-value. Remember how we write our probability statements for p-values. Again, this is a less than test. We have a less than or equal to. In that probability statement, we can go to Excel to get the exact p-value. It is less than alpha, so we have confirmed that we didn't do anything too wonky there. And then again, we just kind of finish it off like usual because our test statistic falls in the rejection region. We have a small p-value. We reject the null. Because we reject the null, that means we can't conclude the alternative. And this is where we just got to do a little extra thinking here. What is the alternative? The alternative is that the mean of the differences is less than 0. And so that means that one mean is actually less than the other, which was kind of our initial question. Is the average reaction time of one hand less than the other? And so that's how we're going to write that out for our alternative.